Uh, yeah, see, as always, unmute yourself and ask a question if you have it. We're going on to Bluetooth. And I thought I'd do my demo first because it worked a couple of seconds ago, and that's the way demos are. It's a difference between being a professor and being a real engineer. It only has to work once when you're a student or a professor, but once you're a real engineer, it has to work forever. All right. Any questions before we get started? All right. I'm going to flip my thing around to the other one. Okay, so I'm going to do basically the same demo 3 times, okay, and show you 3 different perspectives of the, and it will become more and more obscure, I guess is the right way to say it. Oops, come back here. All right, so this is my phone, running Light Blue. It's a free app. I will show it to you in the second step, but down here is a CC2650 and an MSP432 running a starter code, a Lab 3 starter code called Application Processor. There's the name of this device. It's called Shape the World, number 1. And so I am going to this is the advertiser, this is the initiator. I'm going to initiate, which will pair the 2, okay? So now these 2 are paired, and it's not a very powerful application, but it does allow you to look at stuff. And in particular, I am going to run 3 different characteristics, and I know the slides will tell you what those were. This is a write or read-write characteristic. And so if I push this read again button, okay, you see the light screen over here? Okay, take my word for it, it's green. If I read it, it becomes yellow. It basically cycles. Okay, push it with the other finger. You can see it better. Okay. Every time I read it, it changes color. All right. I could write it and it would set the color, but okay. So the next one is a characteristic which is read only, and this one is the switches. So let me read it. And you can see the switches are 0. I'll push one of the switches, and then you can see, I don't know, I can see it. Can you see this says 1 right there?
Yeah, we can see it.
Okay, all right. But basically, as I will explain in the slides, characteristics are essentially shared global variables. Let me do one more, and that's called notification. This is a notification characteristic. And so I am going to listen for notifications. Okay. And what this is now going to do is stream, now not very fast, up, once a second or once every other second. It's streaming data, in this case, the switches. Oops, I don't know what it's streaming. I don't know what it's streaming. We'll look and see what it was streaming. Oh, button 1. That must be this one. Well, whatever. Yeah, there it is, button 1. I just didn't push it hard enough. You can see now this particular button is sending a 1 over and over again. And then I let go, it'll send a 0. So it's a low bandwidth streaming operation. All right, so that was sort of view number 1 from the highest level. You have an IoT device with input output on it. You have a cell phone or another IoT device. This is the master, that's the slave, and you can communicate data between them. Okay, so let's go back over to here. Let's go share screen. Okay. Next, I want to show you the perspective of the debugging. Okay, and so now what I'm going to do is I am going to observe the behavior. Let me go ahead and shut this off so you can watch it happening. Go back, go back. Okay, so now I'm no longer connected, and I'm going to clear this guy here. Clear it. Can you see my black screen?
Yes.
Yeah, big black screen? Okay, good. All right, so I'm going to reset button over here. All right, and then I'm going to clear it. All right, there we go. All right, and then I'm going to hit the reset button again. This is what it takes to establish a Bluetooth advertiser. Okay, this is if you look at the little code, SNP is is a shortcut for the um, standard network processor, which in this articulation is the CC2650. And LP is the launch pad, or the MSP432 launch pad. Okay, and then in order to establish a connection between the 432 and the 2650, it goes through this song and dance using a protocol called application processor. So there's an application processor, which is essentially a set of functions which running on the 432, and the network processor, which is on the CC2650. And we'll talk about the syntax of these protocols when we get to the PowerPoints. But these are UART frames, if you'd like, from the, okay, this one here is from the 432 to the CC2650, and that's the response. Again, and this English is just what it is it's doing. It's resetting, it's getting the version, it's adding a service, okay? And we'll talk about what services are. This is the general GATT service. And then after we have a service, we will add characteristics, okay? And so we have we're going to add a characteristic. We're going to describe what that characteristic look like. And then we're going to add another characteristic and another characteristic and another characteristic over and over again. And so, okay, there's two of them there. Sorry, I must hit the reset button twice. But there's a long song and dance. We'll show you the software third. But it's setting up the communication framework, okay, around which these this device exists. This is defining the behavior of the IoT device as a service and a list of characteristics. Okay, I think there's 5 or 6 of them that were set up in this example. Okay, so once I've set the characteristics for the service, then I will register that service. Okay, and again, this is nothing, no communication is happening yet. This is because I haven't turned on the phone. If you remember, my phone is still off. It's now in power save mode, but my phone is off. And now it is advertising. You can see it there on the phone. It is advertising, but I haven't, because I've got to the bottom of this. So I've registered it. You can, part of the registration is you give it a name, you give it an advertising string. What's my name? Like in this case, it's Shape the World 001. And then once you've established all of the behaviors, you start advertising. Okay, so this is clearly reset somehow. Let's clear it again. Oh, I see. It didn't. Oh, it didn't. Okay, I want to clear the data. Oh, I don't care. It don't matter. Okay, don't matter. And so now I'm going to show you what happens when I initiate a commit. So what just happened is the initiator, which is the phone, made a link, an establishment with the advertiser, which was the CC2650 432 combination. Okay, And so when it's time to do crap, okay, again, the phone is the master, okay? And so when I initiate a response, I initiate a request, okay, then I get this two-step sequence. You notice it's the other direction now, okay? When I pushed a button on the phone, I will get a message from the 2650 to the 432 that says, I'm trying to read, and embedded in here is the characteristic number that I'm trying to read from. And then there's the response, okay? And now it's gonna read, right embedded in there's the actual data that's being sent back to the phone. You see the 3 here in the black, and you see the 3 there on the device. If I do a write characteristic, okay, if I write the number 5, okay, did I hit done? No, done. Okay, you will see that there is a write characteristic here. Okay. Again, from to the device, and there's the 5 coming from the phone to the launch pad. And then there's this particular thing after it does a write, it does another read. But that's just weird. Okay, let me do the notification. Okay, I'll just do the button here. When it sets up to listen, you can see that it's established, and now we're going to get, periodic communications. Okay. Now this is slave initiated. Okay. So the notification says, "Hey, IoT device, send me data periodically." Okay. So you'll see that this is initiated by the slave. Whereas most of the other, here I'm pushing the button, and embedded in there is the button is now pushed. Right here you can see the button was pushed. Right there was I pushed, and there I let go of it. All right, let me do it a third way. Okay. Stop share here. Share over here. Okay, I'm gonna shut the phone down. I'm gonna reset the device. Shut the phone down. So we're not connected anymore. We're not connected. I'm gonna open this one up. Okay. And we're down a huge rabbit hole, but I've got my CC. Can you see the other screen? Yeah, that's one you can see. Oh yeah, here it is. I've got my 1352R connected as a sniffer, set up to sniff Bluetooth. Okay, all right, and it's running but not connected. And then I open up my Wireshark, and that thing will connect. Over here, you see it will. Where'd it go? Here it go. Come back here. Here. See, it's now. You can see it's now open. Okay, so go back to Wireshark. All right, so this is the device. This is the IoT device. Really bored. It doesn't, it's very unhappy that it's not connected to anything. So it's broadcasting, advertising. Sorry, it's advertising its existence, and fairly frequently. You can see it's happening once or twice a second, that it's sending out, "Hey, I exist, somebody connect to me." Now, I haven't filtered this, so every once in a while, my monitor or my laptop or somebody else in the house will throw a Bluetooth tag. But look at what happens when I connect it. Where'd the phone go? Here it is. Okay, so now when I connect it, you see it's going to be, once I connect it, okay, I just connected, the advertising went away. And now what I'm doing is the ability to, now I haven't quite figured out which one of these is which, but let's just stop and look at one. But these are packets being sent between the phone and the device, because you can see they're all these are connection tabs. You notice that the source MAC addresses are one of the two. One is the phone, and the other is the IoT device, and they're talking to each other about happy stuff. Okay, and so it's not a. I mean, every once in a while, somebody else chimes in and makes a mess. This particular packet sniffer wasn't very useful. I couldn't really debug with it, but the other one, the outputting from the two devices was actually quite powerful. All right, stop share. All right, so that's my demo there. Let me go back over here and show the face. Okay, share screen. Okay, that should be stopped sharing. Share screen over here. All right, okay, stop that. Close the session. Oops. If you want to follow along, you're going to have to go upload it. There we go. I've been editing this one. Nope, it's the first time I uploaded it. Okay, there's today's lecture. Okay, go back over here. All right. Well, this is the second of the four major things I wanted to get done. So here we go. As you can see from my demo, the particular lab configurations that I've put into checkout for your lab 2 was the CC2650. I don't particularly care which BLE. It doesn't actually have the most market share, but I figured it out, so that was close enough. Okay, so before I get into Bluetooth, we just like to see where it fits in the space. I could have put sub-gigahertz in here, but we're basically going, you've got, in terms of bandwidth and bandwidth power, okay, power and distance. Okay, it's really how to. So we're climbing the ladder, so to speak, from the lowest bandwidth, the lowest power, the longest distance for the sub-gigahertz. Zigbee fits in there as an example of the IEEE 15.4 protocol. So Zigbee was higher bandwidth than our sub-gigahertz channel, and Bluetooth low energy is higher than that, and Bluetooth standard rate will be higher. And then we get into Wi-Fi, and obviously the cap's the limit. Okay. To remind you that we're in the microwave range, and so, oh my, somebody messed up my thing. That should have been a lambda. All right. Oh, I see what happened. It's just cut off. Okay, hold on. Yeah. Sorry. Capital. Oh, it capitalized it. Stupid. I put a stupid Microsoft. All right, I get what happened. I put a space after it to make it look pretty, and it changed it to a capital. All right, so remind yourself that Don't just think about frequency, think about wavelength. Um, uh, and when we get somebody to teach you antennas, the dipole antenna will have a distance of 1/4 lambda in it. Okay. And now to compare Bluetooth low energy, which is the the CC2650 and the Nordic chip, which I have one slide of. Again, they both exist in the same frequency range, right? They're both 2.4 gigahertz, okay? But they are not the same because they, they will use a different modulations, okay, and different frequency separation. So I got a slide for it in a moment, but the Bluetooth low energy separates the channels at a 2 megahertz rate, whereas Bluetooth, basic rate is a 1 megahertz separation. Okay. It is that Gaussian frequency shift key with a character rate of 1,000,000 symbols per second. Okay, and if you want more symbols per second, you're going to use a different encoding here to get more per rate. We saw from the demo that that the CC2650 is what we classify as the advertiser or the slave, and it will once initiated, once it's initialized, it will sit there advertising, and you can set the advertising rate and all the advertising parameters. Again, I'll show you this the C code at the end, and then when you run Bluetooth low energy, when you run light blue or BLE scanner, you run an application, you can run it in scanner mode and just look for advertising packets, look for advertisers without the intention of connecting. Okay, but once you push the symbol on the phone, it will switch from scan mode to initiator mode and make a connection. We're going to focus on low energy because it's more of an IoT thing. But as I said, as you saw from the previous slide, regular Bluetooth is called either basic rate or enhanced data rate. By using other encryption techniques, you can go faster and obviously more power. There are other methods. I didn't see a lot on this one, so I don't really have much to say about it, except that the trouble with a class like this is everything we do now is pretty much already obsolete. We mentioned the word stack before, and here's another one. Often when you see these stacks, it's compared to this, way back in the 60s or whatever, somebody defined what a network should look like in terms of layers. This open systems interconnect standard model has these 7 layers, and most actual implementations will compress a bunch of the layers into one, and so this in Bluetooth is also compressed. But we will have a physical layer here, which is the radio, and a link layer. Okay, and again, these two are happening in the CC2650. Okay, and then the transport layer, the network layer, all those sort of things will happen up higher. And so in particular, we will see that again, the link layer and the radio are in the 2650, and the GAT and that there is a a line here where you got the MSP 432. So you're going to see the higher levels in this 432 code, but not the lower levels. Okay. I actually showed you this slide last week, and just to remind you that if you're in the 2.4 gigahertz range, so is everybody else. Okay, so this open unlicensed, okay, so this is an unlicensed band. You don't have to pay money to use it, and it's called the Industrial Scientific Medical band. And the problem is it's very busy. Okay, and so there's a whole bunch of techniques to exist in this crowded space, and that is to have channels. Okay, and this particular slide shows you how to interact. How would you coexist with other BLE devices? Okay, how do you coexist with other BLE devices? And that is, you're going to frequency hop. Okay, and so 1600 times per second, you're going to hop to another frequency, and eventually you'll find one without a collision. Okay, and the other thing here is you see that there are some, if you're coexisting with Wi-Fi channels, there will be some channels which don't overlap with Wi-Fi, and those are the purple ones. Okay, so the purple buttons, the purple channels will be preferential for BLE if you're around a lot of Wi-Fi, because the Wi-Fi channels are wider and encompass more of the bands. And again, this all happens in the link layer, down in the link layer. The hopping occurs down here in the link, in the data link. We didn't do Zigbee, but we can compare it to Zigbee. And okay, this is frequency hopping here. Zigbee doesn't have to be in 2.4 gigahertz, but it could be. It could be down in the 915 megahertz, depending on how you initialize it. But you can see the bandwidth is, the bit rate, how many bits per second, is slower than BLE, and the encoding is different. Okay, so these are both phase shift protocols, right? We did them earlier. This was the offset phase shift encoding. But they all have channels, okay? And so again, the purpose of the channels was you to either systematically or manually find a place where you can communicate. Okay? So again, Zigbee, Wi-Fi, and Bluetooth all exist in that 2.4 megahertz area. This would make an interesting, this would make an interesting quiz question. You ready? Got your pencil out. If you're a Bluetooth low energy receiver listening to a Zigbee packet, what are you going to get? Okay. If a Zigbee transmitter sends OPQSK and the Bluetooth receiver is receiving GFCK, what's going to happen?
Gibberish.
Gibberish. Yeah, they don't coexist. Okay, you can't. If you're in the same channel, right? If you're running, they may be at different channels, right? Because if your Zigbee is over here and your BLE is over here, then they can coexist. But if they happen to be in the same frequencies, neither will work. And the trouble is they're not necessarily designed to coexist with each other, right? They are, okay, so I'll get somebody to come teach you antennas, but I do believe this is a quarter wavelength. And this is the printed circuit trace on the 2650 boards. I don't know why it's that shape, but it's apparently it's I've seen it more than once, so must be a good idea. This is what I was trying to see with my sniffer, unsuccessfully, of course, but again, I don't need you to memorize these packet sizes, except they all have packets, okay? Embedded in there typically is a preamble. Yeah, it's a preamble, an address scheme, a address sort of size, and some checksums, some sort of checksums at the end.
You do have to take those into account when you compute your transmission unit, though, right?
Yeah.
The overhead.
Oh yeah. No, these are all overheads. As a matter of fact, yeah. If you saw that, okay. I don't know if it's still there. Hold on. Is it still there? And it's still there. Okay. Turn that back. Okay. Escape. Oh yeah, it's still there. Let me put. Let me go back and show you. Okay. Yeah. Just go. Okay. Stop sharing. Share. All right. Okay. Can you see my sniffer going? Okay. Stop here for a second. So this doesn't go down there. Okay. This is a Bluetooth. This whole thing is a Bluetooth packet, right? This whole thing down there is a Bluetooth packet, okay? And yeah, 93 bytes of stuff. And as we saw, we were sending like 1 or 2 bytes of communication. So 1 or 2 bytes of communication were actually transmitted, and whatever 93 bytes were needed to encode all of this stuff down here. Now, again, I haven't been smart enough to figure out what all this means, but this is, all of these have the same. If you look at the first 2 bytes are all the same. 4500. That's probably a preamble. Yeah. So when you consider, the throughput rate, okay. Obviously, the longer the packet, right? The longer you make the packet, so that would be an interesting quiz question, and that is, if I sent, whatever 1,000 bits of data with this protocol, I guess I wouldn't ask you that. That's weird. But the point is the actual effective bit rate goes down when you add all this other stuff. Absolutely. Yeah. And that's true of all of them, but the most simple. Okay. We saw the advertiser was the one who advertised, but now there's also advertising, which is the act of the advertiser to say I exist. Again, that will be the CC2650. Scanning, I'm just reading the terms out of the book. Scanning is the process of looking to see who's out there. Initiating is what happens when you push the button on the phone to connect to one of the BLE devices. And then once it's connected, the initiator becomes the client, the master, or the central device. So these are all meant to be the synonyms. The central device, the client, and the master are all meant, an initiator, are all meant to mean the same thing, just different words for the same. The advertiser becomes the peripheral, is the server or the slave, and in our case is the 2650. Standby is when you shut it off. You can shut the thing off. This is a little bit different. I don't remember where I got this from, but this is a block diagram for a BLE device. The only real difference in these two state diagrams is that on this one, the scanner can become an initiator, whereas in that one, the standby can become an initiator. I suppose it doesn't actually matter if you go into standby mode before you go into scan mode. So the CC2650 comes up in standby mode, goes into advertising. And once this phone connects to it, it will then become connected and become the slave. Okay, that's the state diagram for the 2650. The phone, okay, goes into scan mode, and then one way or another, it gets into initiating and then becomes connected. And that's the phone. We saw it in the demo, but the essence of Bluetooth, okay, if you want to define it in its most simplest terms, is their shared globals. Okay, there's a global variable in the client and a global variable in the server. And the essence of Bluetooth is to match them, okay? And so the effort of writing is the systematic client-initiated action of syncing these two global variables. So we'll see a write operation initiated by the client will cause the global in the client to be sent to and written to the global in the server. Okay. And again, we got another client initiated event called a read. Okay. Again, it's client initiated, okay, which is the action of syncing these two global variables to match. Okay. And then we had the one more as a notify. So these are client initiated. And then we have one more, which is a notify. Now, obviously, the client is going to, the client will initiate the connection, but once the initiation has established, it's server initiated in this direction, server initiated. Okay, so global variables have a bunch of fields. Okay, and the fancy name for the global variable is characteristic. Okay, sorry. Characteristic is a global variable that can participate in these three actions: a client-initiated write, a client-initiated read, or a server-initiated notify. Okay, and so the notification may be regular, or it may be you know, if the temperature gets too high, I'll notify you. Something. It could be it could be an asynchronous event. So there are, we will see when we establish it, there are fields, there are sub informations for each characteristics. And illustrated here is, there's a bunch of them, by the way, and here's just 3 of them. It has a unique identifier. It turns out FFF, you know, 0, 1, 2, 3, 4 are the ones that nobody cares about, that they're not standard. These are your sandbox numbers. So we'll use the sandbox numbers. So there is a unique unit identifier. And so all of the characteristics in this particular slide are different. You see, they're all different. And then they have a type. And the type could be read only, write only, and read write. So the demo, the first one that I did with the LED was a write only. The second one I did with the button was a read only, and the third one I did was with a notify. And I didn't do any write only demos, but you can have one. And then we have its name, okay? And often what we have is, you know, something that's user friendly. You can see the phone could see the names of the characteristics. And then there's a name. There's more. There's size. There's units. There's a whole bunch of other things that are in here. Okay. Okay. So once you know what a characteristic is a global variable that's shared, that can participate in one of 3 actions: client-initiated write, client-initiated read, and a server-initiated notify. Okay? And then if you put a bunch of characteristics together, we're going to call it a service. And if you put a bunch of services together, that's a profile. Okay? So a profile is a bunch of services, and the particular profile that's implemented in this starter code is the generic attribute profile, which means it's not specific for any, it's just an open-ended sandbox kind of thing that you can play with. Okay, that's what the GAT is, the generic attribute profile. So a characteristic is a variable, a service is a collection of variable, and a profile is a collection of services. In this case, we only had 1 service and whatever bunch of characteristics and 1 profile. Here are some, I downloaded this from Wikipedia. Here's some existing profiles. Again, a profile is a collection of characteristics. Okay, a profile is a collection of characteristics, and if you join the various you know, development consortiums like Health Alliance Consortium, then you can either use or create profiles that other people can use. So once you have a standard profile, you can make a blood pressure device that can talk to others. You can make a blood pressure server, something that collects blood pressure, and connect it to somebody else's you know, client, and vice versa. And the same thing in the fitness device. If you're trying to create a new Fitbit kind of Apple Watch kind of thing, you can join the appropriate consortiums and either use an existing profile or create new profiles for that consortium. Okay? There are profiles for creating networks, right? Now what we've defined before was the fact that a BLE is a pairing between a client, the phone, and the server, your IoT device. but there are profiles that allow you to connect more than two together in a mesh. That's what, basically to create a network of BLE devices. And again, these are standard profiles that you could, okay, I forgot to do, I did, okay, right here, open, okay, so I gotta open this up, stop sharing over here. Stop sharing over here, start sharing over there. Okay, yeah, you can see it. Okay, so I am, yeah, let me open ap.h. Here we go. All right. Again, in this starter code, the 432 is the application processor, and the CC2650 is the network processor. Okay, but before I go in, I want to just go to the bottom of this. When I was creating these starter code, and I was copying this stuff from some source that yeah, there we go. Okay, I left it. Okay. You shouldn't be stealing stuff without leaving the what you call it, the actual source. Okay. Now remember, characteristic is a what? What's a characteristic?
A variable.
A variable. Okay. And one of the fields that a characteristic has is its unique universal unique unit identifier. Okay. And so this enum here is a whole bunch of predefined standard characteristics that somebody else before we got here defined. Okay, so if you've got a current time characteristic, you're gonna give it this UUID, and that means if you use the same UUID as someone else, you can communicate. So there's a 16-bit value you can see, plenty of open space. Well, at least I don't know how many. Okay, so then, okay, that was the characteristics. And then we saw that one of the fields, one of the specifications for a characteristic is its size, right? Is its format, if you'd like. And here's some, yeah, it's good old 12-bit format. Yeah, I don't know how that works, but you could have one if you wanted. But yeah, we used the 8-bit format and the 16-bit format in the starter code. But you can have signed and unsigned and floating point and double floating point and all that. And the other one that I said a characteristic has is units. Okay, so this is especially important, obviously, if you're communicating between devices that have different, made by different manufacturers. Okay? And obviously, you can tell from the name that these are all predefined in this generic GAT. Okay, so a bunch of units. Okay, so that's enough of that. Okay, I showed you that. Okay, yeah, it's stop sharing over there. Okay, start sharing over here. Stop sharing. All right. This is a zoom in of the slide that we saw in the first black and white slide we saw from the book of the stack on BLE, and again, the lower layers are down in the 2650 and the upper layers are in the 432. So you'll see in the 432, we set up the profile, which includes the service, which includes the characteristics. So we're using the GATT profile in setting up the services and characteristics. This doesn't surprise you. What's the difference between Bluetooth low energy and Bluetooth regular rate? One is lower energy, okay? And so how do you manage low energy? And we've seen this slide before, is if we can sleep most of the time. Ah, crap. No, this I probably can't even edit that. Whatever. Yeah, that if we can sleep most of the time, we can bring it down. So one of the things that happens when you advertise is you set up the rate in which you advertise. And so if you want to save energy, you can increase the time between connections, whether you're sending and receiving data or whether or not you're advertising. Okay, so the strategy here is to sleep most of the time. Now we're going to get specific. Here's an interesting thing that I said, okay, that isn't always true. Okay, so way back when we were doing the sensors, okay, just to remind you, like the IMU, like the temperature sensor, okay, the one that had the I2C, the ones that had the I2C interface, what was the general philosophy for producing high-powered, low-cost? So you want a high functionality, you want lots of function, you want small size and low cost. That was our requirements for creating sensors in the IoT field. How did we do that? What was the general approach to developing sensors for the IoT market? You remember?
What was the question? One more time.
Okay. We talked about a bunch of sensors earlier, right? The temp 117, the HDC 20 something 60, the BMI 160, the BMM 150. There's a bunch. There was a bunch of sensors. The OPTs 3101, the OPT 3100, the optical sensors. We saw 6 different sensors that solve this requirements: high functionality, small size, low cost. And how did it do it?
Quantity.
Okay. Okay, so we make okay. If you do have a high functional, small size, low cost sensor, people will buy a lot of it. Okay, but how did we make it high function? How did we make it small size? And how did we make it low cost?
Higher frequency.
No.
Hundreds of thousands of man hours of cumulative work.
Okay, but what were those people doing? If you wanted to make a new sensor, who would you hire? Okay. What is it? What are in those 4 blocks?
more hints? I don't know. I
No.
feel like we're,
Okay, the most important thing you're supposed to remember, and we did about sensors, is it was a single chip. Okay. Okay. So how do you make it small size? Let's go with that. How do you make something very small?
Etching.
Yeah, you integrate it onto a single chip. Okay. That's how you make it small. How do you make it low cost? Is you remove the you remove the human from the manufacturing step, right? You want to remove the gold. Every time you got a connector, you got some gold plate somewhere, or silver, or whatever you gotta, or even tin, you gotta plate it. Okay, so we're gonna put it on a single IC. Okay? And so, what was the first block of a sensor, single chip sensor?
Some sort of analog.
Analog. Thank you very much. Somewhere we have we have signal processing, which is either analog signal processing or digital signal processing, and we have analog to digital converters, and then the last one is the communication interface. And so all of these sensors and many more fit into this architecture, a mixed signal, analog front end, integrated circuit, okay? And I made a general comment. So I still think that's the true statement, okay? If you want a sensor system, which is highly functional, low cost, therefore high profit, because it's fully functional and low cost, you're gonna have a mixed signal, analog digital IC, okay? I made a general comment about IoT devices, right? Things that have radios on one end and have regular computers, embedded system on the other end. And so what was my general statement about IoT devices? In other words, how do you make it fully functional, small size and low cost?
I mean, the same things we just talked about.
It's the exact same things. The exact same things. You're going to integrate the analog front end with the analog signal processing, with the digital signal processing or the communication signal processing, together with the high-end devices. So that part is still true. We're going to use as many single chip entities as we can get away with, because if we can get it fully integrated. The only mistake I made last time was to say the right way to do it is to have 3 processors. Okay, the CC1352R, the CC1310, the CC2650, and the CC3100, which we'll do next, all have this single integrated device, which has a microcontroller. It has an analog front end, signal processing. It looks like a microcontroller on one end, and it looks like a radio on the other end. That's all true. The Nordic Semiconductor BLE device that's got a slide coming up doesn't have 3 processors in it. So I will stand by that. The ubiquitous thing about solving IoT at the front end is to integrate the radio with the microcontroller. Okay, that is as a combination of analog front end, high level. So you're going to implement as much of the stack as you can in hardware, so it's abstracted, but then do your high level protocols with a standard processor that looks like a regular microcontroller. The only difference is when we get to the Nordic Semiconductor chip, it won't be 3 processors. All right. Again, you're interested in the quarter wavelength of this signal as you build this antenna. Okay. And yeah, I don't know, any analog circuit designers in the room? Good.
A long
Because I'm
time
going
ago.
to ask you, you are?
I mean, the optical
Good.
photodetectors and things like that.
Okay, so maybe you know the real answer. So I don't actually know the answer. I'm just guessing. Why is this circuit not in the chip?
I think the inductors are the limiting factor.
Yeah, I don't know if you can put an inductor in a grid circuit.
I mean, you can. It's just footprint, right?
Okay, I don't know. Don't look at me.
Well, it is.
It's obvious. I don't know the answer to that
Yeah.
question. I just posed it without knowing the answer.
Yeah, I second what Austin said from some of my internships. Inductors are really big.
Okay. Obviously, this thing is tuned to 2.4 gigahertz. Obviously, the L's and the C's somehow match to get 2.4 gigahertz. So like I said, I can zoom in to show you some of this. Let's stop. No, stop. X. Discard. Okay. Yeah, okay, that'll work. I was too lazy to find a prettier picture. There we go. Okay, this is the Nordic Semiconductor. Where is it there? The 52840. It's got a huge market share. And so I thought it would probably be remiss if I teach a whole week on BLE and don't mention the most popular chip out there. But it is it's got some stuff similar to other, it's got an architecture similar to other Cortex M's. It's got 2 buses. Why? Where's the ROM, by the way?
It's a Harvard architecture.
No, it's got 2 buses. I don't know. Where's the ROM? I'm looking for the ROM. Yeah, we got to find the ROM before you can tell me it's Harvard architecture. Those are the RAMs. Where's the ROM?
Is it the code block on the right side?
Maybe. Okay, so if this is the ROM, then it is a Harvard architecture, right? It fetches opcodes out of the same bus as it fetches data. But nevertheless, it satisfies most of what I mentioned 2 slides ago, and that is it has a front end. Okay, where'd it go? It's got an antenna interface, an analog front end. It in some ways looks like a microcontroller, right? A to D converters, I squared C, I squared S, SPI, UART, pulse width modulation, all the standard stuff that looks like a microcontroller integrated with the analog front end. Okay, clocks, thermometers, timers, all that sort of stuff. And then if you type this number in and go to the buy page, there are dozens and dozens of development boards that you can buy for this chip, okay, or different versions of this chip. Yeah. I have not used it, although my previous 2 PhD students who started their own company who made basically a fitness device, built it around this particular chip, and they really liked the development package for it. One of these days I'll learn how to use it. Okay, so I'm just, again, I don't want you to think I have a vested interest in Texas Instruments. As a matter of fact, if you were going to build a Bluetooth device, please evaluate this particular family of devices. As far as I can tell, they got a pretty big market share, and that doesn't happen by accident. That being said, we'll go back to the 2650 and remind you that the client is the phone. running an application like light blue or BLE scanner, and then they're basically the read request and the write request are initiated by the client, and the response goes back. Okay, so there's always a 1-2 yes, okay, kind of a command response communication. Okay? There are in the lab for lab 2, there are two 2650s. The 2650 on the robot is this booster pack, 2650 booster pack. The 2650 on the fitness device, the one that has the accelerometer and the graphics, is a 3-board stack. When the bottom board is a 2650 launch pad. And obviously their intent with a launch pad was to do BLE with a single chip. And I find it inappropriate or very difficult to require undergraduate students to learn TI-RTOS. Okay, now grad students, I don't care. You guys are smart enough to figure it out. But TI-RTOS is a beast to understand. Fully functional and wonderful as far as operating system is concerned, but not something you want to teach an undergraduate in a day. So we programmed the 2650 Launchpad with that standard network processor, so it behaved like a 2650. Oh yeah, I should write. You can quit and remind you that if you do one of these labs, the pins aren't the same. Where's my insert? Check them. You know, it's written all over the lab manual, but the GPIO.H configuration, it's like the word default, I think is what it's called, are different. And I don't, you know, so for example, in the CC2650, in one of them, the master ready, slave ready is here, and on the other one, it's somewhere else. So the actual position of the pins is different for those two different lab configurations. Okay. It's a handshake protocol. Again, it divides the stack into two places. The 432 is the high level, 2650 is the low level, and the communication protocol is handshake serial. Okay, and so if it's a master, again, if it's a 432 initiated transmission, it goes over here, 1 2 3 4, 1 2 3 4 5, handshaked, and that's for information going this way. It's possible for information to be triggered in the other direction. In other words, when you hit the phone, when the phone hits, you hit a button on the phone, the first thing that happens is data's going that way. And so the slave ready goes low, the master ready, 1 2 3 4. Highly reliable. You know, collisions cannot happen. There are timeouts, so that if the master ready drives its low and the slave ready doesn't go low, it'll time out. Right? If the master ready goes high and the slave doesn't go high, there'll be a timeout, so that it will crash fairly gracefully. Well, it crashes. And that timeout is usually a function of the fact that you didn't have this set up. Okay. So if that's not set up right, it'll cause timeouts in there and nothing happens. How do we set things up? What time is it? Okay. We create a service, we add characteristics to the service, and then we add it. Um, uh, um, the gap is where we do the advertising. We set up the advertising data, and then the device waits. And as I mentioned, there are three things that the slave does. Is it if the client initiates a read request, it satisfies it. If the client initiates a write request, it satisfies it. And if a notification is set up, it will perform. So this is the low-level protocol that is set up between the 432 and the CC30. Again, this is a serial communication between the two. Yeah, and there is obviously a start and a checksum code as sum of all the other datas, and they all begin with length and command, and then the variable part is the payload. Okay, and so here is an add service with the service name, FF F0, little Indian. Okay. This is a read indication. Again, this is coming from the phone to the device. And so you push your button on the phone, it sends a BLE read request to the 2650 to 2650, sends it to the 432. 432 responds. And then one byte of data is sent back to the phone. Okay. I don't know, the data sheet for this was 100 and something pages long, and embedded in there were all of the codes here for what all these protocols are. This is a read indication. The things have handles. When we create a characteristic, it gives us a handle, and that handle. Okay, so I did ask that question before. What's a handle?
A pointer to an object.
Yeah. A handle is usually more than a pointer to one piece of data. It's a pointer to a whole bunch of stuff. And so this is a handle to the characteristic number 21, and embedded in that data structure is all the information about that characteristic. Okay. So rather than, rather than sending all it, then yeah, okay. So, which says, we started out with million bits per second. We're obviously going to go way slower because we got to send all this crap from the phone to the 2650, and all this crap from the 2650 to the 432, and then all this crap from the 432 to the 2650, and then this thing has to be sent back again. Okay, so again, there's a packet from the phone to the 2650, and then that's one, and then two, then three, and then four. Then there's a packet from the 2650. 2650 back to the phone. Okay. The write indication looks very similar, except the data shows up there, okay, on the incoming, on the incoming. Yeah, demo. I did my demo. What time is it? All right, I'm gonna stop here. I probably will show you what I haven't shown you yet is the actual code on the 432. It's pretty straightforward. Yeah. And then, yeah, we'll go on to chapter 6. All right. So what's left to do is to show you in the Code Composer Studio, I'll show you the application processor.c and the application processor.h. Yarabali and I made this chapter 6 in one of our MOOCs. And so, I don't know. It's a little bit more superficial than what we're doing here. So I don't know if there's anything in there that's of value. But that's where we did this one for the first time. Questions? I'm almost done. Let's see. Well, yeah, does anybody want to contact me about the project? Have any questions? Oops, no.
Were we supposed